Alright, let's talk about something that might not sound glamorous but is critically important in countless plants across America. I'm talking about steam control valves. Imagine you're running a massive industrial laundry, the kind that cleans linens for every hotel in the city. Your whole operation depends on a steady, reliable supply of steam to power the presses and dryers. The humble control valve is the gatekeeper of that steam. It dictates how much energy gets to your equipment. Get the size of that valve right and everything runs smoothly, efficiently, and safely. It's a job that demands respect because when it goes wrong, things get messy, expensive, and even dangerous. So what happens if you get it wrong? Let's say you install a valve that's way too big for the job. You might think bigger is always better, but you'd be mistaken. An oversized valve is like trying to write your name with a mop. It has no fine control. The valve will barely crack open to meet the system's demand, causing it to constantly hunt and cycle. This leads to something called chatter, where the valve plug rapidly opens and closes, rattling the pipes and wearing out the valve's guts, the seat and plug, in no time. This means poor temperature control for your process, premature failure of expensive equipment, and a whole lot of headaches you just don't need. Now let's consider the flip side. Installing a valve that's too small. This is like trying to put out a forest fire with a garden hose. The undersized valve simply cannot pass enough steam to meet the needs of your equipment, even when it's wide open. Your machinery will be starved for energy, leading to sluggish performance and a drop in production. Imagine your industrial presses not getting hot enough to properly iron those sheets. The valve will be working at its absolute maximum all the time, which can create excessive noise and velocity, eroding the valve and the downstream piping. You're essentially creating a permanent bottleneck in your system. The bottom line is that proper valve sizing isn't just a suggestion. It's a fundamental requirement for a well-run steam system. It's about finding that Goldilocks valve, not too big, not too small, but just right. Doing the work up front to calculate the correct size saves you from a world of hurt later on. It prevents costly downtime, reduces maintenance nightmares, and ensures your system operates as efficiently and safely as possible. It's one of those dirty jobs behind the scenes that makes everything else work the way it's supposed to. It's about doing the job right the first time. So, how do we find this just right valve? We need a standard way to measure a valve's flow capacity. That's where a little thing called the flow coefficient, or CV, comes in. Think of CV as a universal rating for valves. It's a number that tells you exactly how much fluid can pass through a valve under a specific set of conditions. It's the great equalizer, allowing us to compare the flow capacity of a 2-inch valve from one manufacturer to a 2-inch valve from another. Without it, we'd just be guessing, and guessing with high-pressure steam is a terrible idea. The official definition of CV is pretty straightforward. It's the number of US gallons of water at 60 degrees Fahrenheit that will flow through a fully open valve in 1 minute with a pressure drop of 1 pound per square inch, or PSI, across the valve. So, if a valve has a CV rating of 50, it means 50 gallons of water per minute can pass through it with a 1 psi pressure drop. A higher CV means the valve can pass more fluid. A lower CV means it passes less. This simple number packs a lot of information and is the cornerstone of every single valve sizing calculation we're about to do. Now you might be thinking, Mike, that's great for water, but we're talking about steam. And you're right, steam is a compressible gas, not an incompressible liquid like water. Its density changes dramatically with pressure and temperature. So, while the CV value itself is defined by water, engineers have developed specific formulas that use this same CV rating to accurately predict the flow of steam. The beauty of the CV is its versatility. It provides a standard baseline that we can adapt with the right math to work for different substances, including the saturated and superheated steam that powers our industries. Understanding CV is the first real step toward mastering valve sizing. When you look at a valve manufacturer's catalog, you'll see CV values listed for different valve sizes and types. Your job is to calculate the required CV for your specific application, your flow rate, your pressures, your temperatures. Once you have that number, you can confidently go to the catalog and select a valve that has a CV rating slightly larger than what you calculated. This ensures the valve will operate somewhere in the middle of its range, giving you the best possible control over your system. It's all about matching the valve's capability to the system's needs. Alright, time to roll up our sleeves and get into the math. Don't worry, it's not as scary as it looks. We have specific formulas to calculate the required CV for steam. Let's start with the most common type saturated steam. This is steam at its boiling point for a given pressure. Think of a pot of boiling water. The steam coming off is saturated. The formula we use depends on whether the flow is critical or subcritical. Flow becomes critical when the outlet pressure, P2, is less than 58% of the inlet pressure, P1. At this point, the steam flow is choked, and lowering the outlet pressure further won't increase the flow rate. For subcritical flow, where the outlet pressure is more than 58% of the inlet pressure, P2 is greater than 0.58 times P1, the formula is CV equals W divided by 2.1 times the square root of the product of P1 minus P2 and P2. Here, W is the steam flow rate in pounds per hour, P1 is the inlet pressure in PSIA, and P2 is the outlet pressure in CSIA. For critical flow where P2 is less than or equal to 0.58 times P1, the formula simplifies because the pressure drop term becomes constant. In this case, the formula is CV equals W divided by 1.61 times P1. It's crucial to use the right formula based on your pressure conditions to get an accurate result. Now what about superheated steam? This is steam that has been heated beyond its saturation point. It's drier and contains more energy. Because it's less dense than saturated steam, we need to adjust our formula to account for the degree of superheat. The formula for superheated steam looks very similar, but with one extra piece. CV equals W times 1 plus 0.0007 times T sub SH, divided by 1.61 times P1. In this formula, W and P1 are the same as before, but we've added T sub SH, which represents the degrees of superheat in Fahrenheit. This factor corrects for the lower density of the superheated steam. A quick but important note, all pressures in these formulas must be an absolute pressure, or PSIA. Your pressure gauges on the factory floor likely read in gauge pressure, or SIG. To convert, you simply add the atmospheric pressure, approximately 14.7 psi at sea level, to your gauge reading. So, a gauge reading of 100 psig is about 114.7 psia. Forgetting this step is a common mistake that can throw off your entire calculation. Getting the units right is just as important as getting the numbers right. Precision here prevents problems down the line. Alright, let's walk through a real scenario to see how this works. So, say you need to control the flow of saturated steam to a piece of equipment. The required flow rate, or W, is 2,000 pounds per hour. The steam line pressure upstream of the valve, that's P1, is 100 sig, and the pressure required at the equipment, P2, is 85 sig. First, we need to convert our pressures to absolute. So, P1 is 100 plus 14.7, which gives us 114.7 psia, and P2 is 85 plus 14.7, so that's 99.7 psia. Next up, we check if the flow is critical or subcritical. We check if P2 is less than 58% of P1, so 0.58 times 114.7 is about 66.5 psia. Since our P2, which is 99.7 psia, is greater than 66.5, we've got subcritical flow. Now we plug our numbers into the subcritical flow formula, CV equals W divided by 2.1 times the square root of the difference between P1 and P2, multiplied by P2. This becomes CV equals 2,000 divided by 2.1 times the square root of 114.7 minus 99.7 times 99.7. First, let's solve the part inside the square root. 15 times 99.7 equals 1,495.5. The square root of that is about 38.67. Now our formula is CV equals 2,000 divided by 2.1 times 38.67. This simplifies to CV equals 2,000 divided by 81.2, which gives us a required CV of approximately 24.6. Looking at a manufacturer's catalog, you'd pick a valve with the next highest CV, probably one rated at CV equals 30. That way the valve operates effectively, probably right around 80% open. Now let's see what happens when we make a mistake. Imagine a rookie engineer tackles the same problem but forgets to convert the pressures from gauge to absolute. They use P1 as 100 and P2 as 85. The pressure drop is still 15 psi. Their calculation would be CV equals 2,000 divided by 2.1 times the square root of 15 times 85. That equals CV equals 2,000 divided by 2.1 times the square root of 1,275. which is CV equals 2000 divided by 2.1 times 35.7, or CV equals 2000 divided by 74.97. This gives a required CV of 26.7. While this number is close to the correct one in this specific case, this simple error can lead to much larger deviations in other scenarios, and that could cause you to select a valve that's too small and just won't be able to meet the process demand. Here's another trap. What if your outlet pressure P2 is much higher than your inlet pressure P1? This can happen if you mix up your gauges or if there's a problem downstream. If P2 is greater than P1, the term P1 minus P2 becomes a negative number. You can't take the square root of a negative number in this context. If you see this, stop. It's a mathematical red flag telling you something is physically impossible. Pressure drop just can't be negative. Fluid always flows from a higher pressure to a lower pressure. It means you need to go back and check your numbers and your understanding of the system's pressures. Doing the math is one thing, but honestly, applying it in the real world is another. Here are a few tips I've picked up over the years that will help you get it right. First, always know your actual operating conditions, not just the design specs. Talk to the operators. Find out the real-world minimum and maximum flow rates and pressures. Sizing for the typical day might leave you short when demand peaks. Second, don't size the valve for the full line size. A 4-inch pipe does not automatically need a 4-inch control valve. In fact, it rarely does. Most control valves are 1 or 2 sizes smaller than the line they're in, which means you'll need to use pipe reducers. Third, think about noise. High pressure drops across a valve can create, well, screamingly loud noise, which is not only a safety hazard for workers' hearing but also a sign of destructive vibration and high velocity. Most valve manufacturers provide software or charts to predict noise levels. If your calculation predicts excessive noise, you may need to use special low-noise trim in the valve or even split the pressure drop across 2 valves in series. Fourth, consider the turndown ratio. This is the ratio of the maximum controllable flow to the minimum controllable flow. If your system needs to operate over a very wide range, you may need a valve with a high turndown ratio or maybe a split range setup with 2 separate valves. My fifth tip is to account for future needs. Is the plant planning an expansion in the next few years? It might be wise to select a valve that can handle a slightly higher capacity than you need today, but be careful not to oversize it so much that it causes control problems now. Finally, and this is a big one, when in doubt, consult the experts. Valve manufacturers have teams of application engineers whose entire job is to help folks like you select the right valve. They've seen it all and can provide invaluable guidance. Don't be afraid to pick up the phone. To wrap this up, sizing a steam control valve is a job that blends science and, honestly, a bit of practical art. It starts with understanding why it matters, for safety, efficiency, and reliability. It really hinges on knowing the CV and using the correct formulas for your specific type of steam and pressure conditions. Always double-check your units, especially converting SIG to PSIA, and finally, bring real-world knowledge to the table. By following these steps and keeping these tips in mind, you can size your valves with confidence, making sure your steam system works hard for you for years to come. It's a dirty job, but, a satisfying one when you get it right. If you found this helpful, please like the video and subscribe to the channel for more content like this.